ignite by a factor of 4 to 1. So it can only exist in the period of time between release and full dispersion. That's the only time that it can reach the LFL. So what we want to do is examine the time that it goes from the initial release to full dispersion. If that time is short, we have a safe design. Els also mentioned what happens in equipment rooms. What I'm really going to talk about today is what happens in the occupied space, not in an equipment room. Equipment rooms are considerably different. We're talking about unlimited charge situations, big machines like our air conditioning this hotel. So we're talking about what happens in the occupied space, but still with fairly large equipment, not room air conditioners, large equipment that could in fact feed this occupied space. Okay, so I'm going to show you some physics and some cartoons that may help you understand. This is the product of about 50 CFD runs. Each one of these runs takes about a week to run with some pretty high-powered computers. And so what you're seeing is just a small snapshot of a whole lot of work that was done by some very smart people to do the modeling. The base case, which really helps us understand, we've got a leak source. We've got a room that is being supplied by that leak source. This represents a direct expansion kind of system. The refrigerant is leaking out and ultimately would leak to the RCL calculation, in other words, 25% of the room. So we're examining the time at which the refrigerant disperses and goes into the room. Here's what the physics looks like. This is an actual run. This is a picture of the output of the run. What you can see is, as the refrigerant is released, much as you've heard before, the refrigerant is denser than air. It falls to the floor. And you can see that the refrigerant concentration at the LFL, 14%, rises to about 12 inches, about a half a meter. So the refrigerant releases, it hugs the floor. The LFL, below about a half a meter, is capable of being ignited, and then full dispersion occurs. How fast does that dispersion occur? Well, the answer is, with no ventilation at all, in about 10 minutes, relatively short period of time, not hours, not days, but within about 10 minutes, the refrigerant falls below the LFL. In other words, by simple diffusion, that refrigerant is starting to disperse. That's a very important thing, because what you should intuitively understand is, if the time is short, the risk is small. Right? If the time is short, the risk is small. So let's build on that. The first case I showed you was magically releasing a charge of refrigerant into a room with no motive force behind it. Now I'm going to add some motive force. I'm going to disturb this. How am I going to disturb it? The first way I'm going to disturb it is with a real leak. I'm not going to magically release it, but I'm going to release it through a hole. Well, this is an interesting problem. Here's what it looks like. Oops, did it again. So here's the equipment source. I've got a leak. The leak is unencumbered. What happens to the refrigerant as it tries to release into the room? Well, here's what it looks like. A very interesting result once again. The LFL, you can see right at the exit of the refrigerant from the broken line, or whatever is causing that leak, is at the LFL. Everything else is above the LFL. The LFL is never reached. You couldn't possibly ignite the refrigerant in a broken tube. Now, I think Kotoka showed us what was happening with a torch and a leak. And you can see some of those dispersions. But what you didn't see was that refrigerant cascading through the room. In fact, it's trying to blow itself out. So again, a very important thing. It only takes a little bit of motive force to have a very safe installation. But we know that this doesn't really happen either. neither can you release the refrigerant instantaneously without some kind of a broken line, nor can you release the refrigerant unencumbered. There's almost always a cabinet with the equipment that's installed in the occupied space. So the answer is somewhere in between, but the point is the jetting effect is a very, very powerful motive force. So again, we move in the direction of safety. Let's add another disturbance. Let's add some ventilation air. Now, we modeled all sorts of different air inlets and air outlets, and this is the case of that's ultimately prescribed by ISO 5149. You want the exhaust air to be as low as possible in the room. So in this case, the ventilation air is coming in and it's leaving through an exhaust as nearly located to the floor as practical. The leak source on the opposite side of the room. What happens in this case? Well, this is really, really, really important. In less than 1 minute, and oops, I did it again. I quit doing that. In less than 1 minute after release, the refrigerant leaves the room, and in the first place, it's only at the LFL at the very, very bottom of the room. Very, very short time periods. So these are inherently safe installations. Okay, as long as you put an exhaust air near the floor, same as prescribed by ASHRAE 5149, you get an inherently safe installation with the equipment in the room. Now, what happens if I take the room and instead of the leak source, instead of putting it on the floor, put it up on the wall? And I think again, Katoka-san showed us some of those results. Let's have a quick look. Here it's located up on the wall. We're not going to provide any ventilation at all. I think what you'll see is essentially this agrees with the little diagram he showed you. Okay, the refrigerant through gravity alone is falling down the wall, and you get a very, very small zone that represents the LFL. But more importantly, once again, it only takes minutes, and that refrigerant pool has dissipated and falls below the LFL. Put exhaust air into that room, and it's gone even quicker. So the time, once again, is very, very short. So again, by design, if you put exhaust air in a room and you put a cassette up on a wall, you get an inherently safe design. I said I wasn't going to talk about equipment rooms, but I will mention it. You know, again, these are very, very large charge systems as opposed to charges that are limited by the RCL calculation. So in this case, we're talking about huge, huge chiller installations with unlimited. You know, we did take a look at some of those cases, and basically, you just have to pump a lot of ventilation air and put the exhaust down on the floor, and once again, you have a relatively safe installation, but I'm not going to go into that in the interest of time. How am I doing on time? Nobody's keeping track anymore. I guess that's good. So here are the, you know, after looking at all of these cases with equipment located in the occupied space, ducted systems, cassettes on walls, all the geometries that you can think of, all the different ways that you could put ventilation air and exhaust that air. So again, a variety of situations. You know, here are the bottom line conclusions. And I think you'll see that these are similar to what you might have already heard, maybe not identical. For ASHRAE 15, we won't have any charge limitations beyond the RCL calculation. That's quite a bit different than you heard in 5149. Very simple to administer. The RCL calculation is woven into the United States design fabric, and so people are comfortable in doing that. We didn't see any need to limit the charge beyond that. I showed you the various spill zones. We want to make sure that any electrical sources, the most likely source of ignition, are located well away from those spill zones. So We want those ignition sources to be above a half a meter in a room, or we want them to be outside of the spill zone for anything that's located on a wall. Inherent safety if you move those potential ignition sources away from the spill zone. Mechanical ventilation. We talked about putting the exhaust air as close to the floor as you can. Many systems are fed by VAV systems, and so we want to make sure that that ventilation air doesn't get shut off. We want to keep it running. We want to have 1.5 air changes an hour. That will exhaust the refrigerant in minutes, and so that's a very, very easy thing to accomplish in a safe installation. I mentioned mechanical equipment rooms. We're using the IR recommendation of 30 air changes an hour. Let me go back for just a second. One difference that we're making this a little different than 5149, because these time frames are so short, if you do an inherent robust design through the kinds of techniques I'm talking about, because it's so short, there's really no need to put up an alarm. The refrigerant's gone in a matter of minutes, okay? So if you put up an alarm, people are going to expect to do something unusual when they enter a room. Fire protection people, emergency response people, we don't want to set off alarms. Refrigerant's gone, okay? Go do something about getting the equipment back online, but you don't have to do anything to mitigate the accident. If the ventilation air is turned on, in minutes, the problem is taken care of. I don't think this is unique, but a little different approach. Honeywell has been doing a lot of work to try and understand, how hot a surface will really ignite these refrigerants in a ducted situation where we have heaters, that type of thing. We don't want any open flames, that's for sure, but in a ducted situation, we don't want any hot surfaces that are above 700 C, and that's a value that could change. They continue to do a lot of work to try and understand the consequences of adding oil and that type of thing to the refrigerant. But it seems that the whole class of refrigerants isn't capable of being ignited except by some pretty hot sources in terms of duct heaters and that type of thing. The second way you can do that is provide a little ventilation air. If refrigerant is accumulated in a ductwork, just purge it. It's safe in a matter of seconds. Last point to be made, again, these kinds of understandings of the physics and ultimately the rules that ASHRAE 15 will write, that's one part of the equation. That leads us to an inherently safe design. But that, codes and standards don't really cover the full gamut. You've heard from other people, every time you do a risk analysis, service rises to the top of the list as the thing you need to worry about the most. Indeed, the good folks at AHRI did some work and sponsored a risk assessment to accompany the work that was done to complement ASHRAE 15. Guess what? Service popped out as the number one problem again. I guess just a personal comment. I've heard a lot of things about training and that type of thing. But the one thing that stands clear to me anyway, as a personal individual who's been involved in more than one litigation, and by the way, if you've ever been in a court case, you get asked nasty questions like, did you do everything that you could have done to prevent the accident? Did you warn the people who were going to be involved in servicing equipment that this is a different, unique situation and they need to do something different? That failure to warn is a real problem. The failure to do the things that you need to do to really get service technicians in the place they need to be for the unusual things that they're going to be asked to do with this equipment, that's real. So I would tell you there's one thing, and above all other things, that manufacturers and regulators need to think about in terms of service, and that's warn people that this is new, different, and unique. Okay, don't hide from the fact that whatever refrigerant you're putting in this isn't an A1 refrigerant anymore. It's something else, and you better think about doing things differently. Failure to warn, the number one problem. Okay, put big labels on things. Let them know it's new and different and unique. Um, I can speculate a little bit about timing. There's been an ad hoc working group in ASHRAE 15 for about 2 years now, trying to understand the physics, look at other things that have been done in the world, reduce it down to code enforceable language. Again, simple, highly inherent design, robustness, simple to use, easy to enforce. That's where we're about. It's a hard process. We go through lots of public reviews. We've been hard at it for a long time. I'm hopeful as chairman that we'll get out for public review this year. This is where we get, all of the rest of the stakeholders involved, not just the manufacturers. We want building code officials to look at it. We want fire protection people to look at it. We've got a close association with UL, which helps us write product standards, not just installation. But here we're looking at product standards. We get insurance companies involved. Guess what? None of this matters unless you can get a building insured. And so it's got to be right, and we want the insurance people to look at it. So, at the end of the day, that public review process is long and it's arduous, and we'll get several hundred comments that in the end need to be dealt with. Last slide. I'll leave the topic of what's going on in ASHRAE 15 for a second, and I guess leave you with one last personal thought. At least in some respects, throughout the course of the last day and a half or so, excuse me, we heard remarks about life cycle climate change effects, and I remember at least one chart alluded to the fact that the actual environmental effect is more a function of the operation equipment than anything else. This is a graph that I happen to pull from a recent Purdue conference paper. It's a heat pump in Houston, Texas, so it applies to high ambient kinds of situations. What you can see is that the life cycle climate change effect is absolutely governed by equipment operation. Almost 96% of the climate change effect is operation related. So while we all have got our hearts in the right spot and we're moving toward lower GWP alternatives, and I think AHRI, Stephen Urich mentioned, $5 billion being spent by a whole bunch of well-intentioned people. I don't think you can leave this room without understanding that those moves to new alternative refrigerant must be accompanied by continual pressure on performance improvement. Okay, don't ever walk away from that one. Okay, in fact, you ought to be demanding higher performance equipment at the same time that you move to more environmentally friendly refrigerants that have a less direct effect on the environment. I'll lean just a little bit on my product development experience. I've got a lot of years at that, the last of which was about 10 years devoted to compressor development, where we looked at a great many things that we could do in the world of new refrigerants. And I can tell you that unless there's a demand for higher performance, you'll never get it. A salesman, he comes to a customer and he opens his catalog and says, here's what I've got. But you have no idea what companies are working on and how performance can be improved unless you ask for it and demand that something change. Don't walk away from that one. So at the same time that you're demanding more environmentally friendly solutions on the refrigerant, let's make sure we're working on the right problems. Let's ask, in fact, not just ask, but let's demand for higher performance equipment in addition to those changes in alternative refrigerants. Thanks for your attention.
Thank you, Dennis. I'm pleased to introduce the last speaker at this session, Mr. Brian Harrack. He's talking about testing of HVAC equipment with future refrigerant. He's currently a director of engineering of HVAC performance at Intertech, and he has been involved in the testing of HVAC equipment for 36 years. His current activity includes the participant of 7 committees of ASHRI and also 5 working groups of ISO. He is also acting secretary of IEC standards, IEC SC61D subcommittee, and also be as secretary of ASHRI standard 37. Let's welcome Byron.
Good afternoon. Luckily, my presentation is quite short, so I will hopefully get us back on track and get us through this rather quickly. My presentation is really 2 quick presentations. It is a very brief overview of what's driving the need for testing HVAC equipment with these new refrigerants. The role of the independent testing laboratory and why the implementation of a certification program would be a very good idea. And then secondly, I'm going into some discussions on what special considerations laboratories need to take under consideration when starting to test flammable refrigerants. First, in regards to safety testing and safety certification of equipment, some of the reasons we need to test and some of the answers we need to come up with is, first, of course, is the unit electrically safe? And what pressures might we encounter in these units, and can the units handle these pressures safely, especially when you're talking about high ambient conditions? Does a unit allow for the non-containment of refrigerant charge if leaked? You don't want the refrigerant to pool and cause a potentially hazardous situation where it could be ignited. You want the refrigerant to be dispersed, as we've seen the diagrams here today. Also, are the components certified for use with flammable refrigerants, and another important factor. Now, when talking about HVAC performance, energy efficiency, and capacity, the things we're going to look at are what types of capacities and ERs are we going to see with these new refrigerants, and again, what are the higher ambient temperatures going to do to affect these capacities and EERs. Also, what kind of operating pressures will be encountered, and can these units actually operate at extreme conditions? Another potential question that can be answered is the acoustics of a product. What are the acoustic values going to do? How are they going to change as the ambient temperature rises? And how do these new refrigerants, of course, interact with other materials, seals, valves, oils in the system, something else that needs to be tested and looked at. And there's all kinds of unknowns that we may be able to uncover. Now, for just briefly going over the role of an independent test laboratory, some of the things that the laboratory can help out with is credibility. An independent third-party test and test report can go a long way in showing your potential clients what your product can do. Extra capacity, independent test laboratory can supplement a manufacturer's labs during periods of high testing demands on your internal labs. And verification, you can double check your lab that you have against an independent source to see how the labs correlate. Market access, you can test to different requirements from different regions, of course, and see how the unit performs under various conditions throughout the world. And programs, an independent laboratory can be used to test to national or regional certification or verification programs where they exist. Safety, and it's to be a independent source of checking the safety and performance of imported products into your country. And also just extra help, assistance with national and regional research projects, the development of product testing standards, and managing through all the complexity that comes with something new, like new refrigerants. The benefits of a certification program. A certification program can build consumer confidence by performing verification, testing, and product labeling schemes. It levels the playing field throughout of manufacturers, and it ensures that MEPs are being met. It can also assure a basic level of quality for all products tested. And it verifies the performance ratings and claims of the manufacturer of each product being tested. And it can be used to settle challenges amongst different participants. Now, to get into a little bit more detail on what you need to do to prepare your particular lab to test products with flammable refrigerants. Some of this has been talked about already today, and this may act just as an overview of some items that may have already been said. But the very first thing to do is compute the maximum allowable charge for each test room. The previous two discussions this afternoon covered that in great detail. The example I have at the end of this is a very simplified version of that, just the very first step you need to take to look at the amount of refrigerants that can be contained in the units under test. You need to check the potential operating pressures of the product that's going to be tested, install new gauge lines throughout the test facility so that you won't have any leaks as far as getting pressure readings on the product. Of course, you need to have separate labeled canisters for each type of refrigerant that's going to be used. And you need to check your reclaimers to make sure that they are correct to handle the new type of refrigerants. We'll also go into a little bit of detail on that. I had here to raise all electrical components to 7 feet or 2.15 meters off of the floor. That may be a little bit extreme, but it builds in a large safety factor when you take any electrical components you have in your test lab and rewire them to be up off the floor. Also, if a test room is not large enough to safely handle the total charge, should a loss occur, then detection and ventilation must be installed in the test facility. And this needs to happen both on the indoor room and the outdoor room of your test facility, because you can never determine where that leak may occur. All the examples we've seen today have been showing leaks happening, on the indoor of a unit, because that's what we're concerned with, in a residence. However, in a test facility, you've got two rooms, they're both enclosed, and you need to prepare that both rooms are able to handle a leak of the refrigerant from the product. Another topic that's been really harped upon today over and over again is the importance of training, and this will be the training of your test technicians and your test engineers who are working with these products and running the tests in your laboratory. Brazing procedures. This is a simplified overview of the training that needs to take place when teaching your technicians on brazing with and around the new refrigerants. Obviously, you need to remove the entire refrigerant charge in case of an unexpected failure while brazing. If refrigerant has been removed, the system should be flushed with oxygen-free dry nitrogen, OFDN, and OFDN should be purged through the system both before and during the brazing process. due to the possibility of explosion, compressed air, or oxygen, must never be used for flushing, pressure testing, or filling the system. When possible, use cold connection technologies instead of brazing for system repairs where residue flammable refrigerant may be present. Reclaiming of the charge. The machine used for refrigerant recovery must be suitable for use with flammable refrigerants with no potential sources of ignition. HFC refrigerant recovery machines may not have been approved for use with flammable refrigerants. Approval must be sought from the manufacturer before using a standard HFC recovery machine with any flammable refrigerant. Some machines may be safe for use with flammable HFCs, but not hydrocarbon refrigerants. A refrigerant recovery machine suitable for use with hydrocarbon refrigerants is available and may be used with other flammable refrigerants. The recovery cylinder must be specifically suitable for the refrigerant used. Refrigerants of different safety group classifications must not be mixed. That's a pretty obvious one. And containers must be carefully weighed during the transfer of the refrigerant. And talking of being carefully weighed, adjusting the charge in a test sample. Some basic rules that need to be followed when adjusting charge. A system with one refrigerant should never be topped off with another type of refrigerant, particularly a flammable one. Very accurate scales are necessary when charging small, critically charged systems with some flammable refrigerants. Scale accuracy must be suitable to the system refrigerant type and the charge size. Many scales traditionally used for HFC refrigerant services may not be sufficiently accurate for use with hydrocarbon refrigerant